Welcome to the Biology 182 lecture on population ecology and how populations grow. Students should be able to explain how species are affected by population size and describe how populations grow at the end of this video. A population is a group of organisms of the same species living in the same area at the same time. Here we see a population of octopuses or octopi, a population of seahorses, a population of sharks, and a population of crabs. When we put all of those organisms together in the ocean, it's called a community. But when we include the abiotic environment with the sand and the water, that's the ecosystem. When looking at how populations grow, we're looking at how the population changes in number between generations. This little delta triangle sign means change in. And so what we do is we take the final minus initial in order to be able to determine the change. So the change in n, which is the number of individuals in a population, divided by the change in time, or months, days, years that we're looking at, will equal the number of births minus the number of deaths. So we can also say that R is the per capita growth rate, which is births minus deaths in a given time period. So if we look at delta N, or the change in number of individuals in the population, divided by the change in time, it will equal the per capita growth rate, or B minus D, times the number of individuals. So let's say we have a population of 137 fish. If 12 die this month, what is the death rate? The death rate would be 12 fish that die out of 137, which is also equal to 0.09. So we could say 9% of the fish in the population died this month. If 7 fish are born this month, we would calculate the birth rate as 7 fish out of 137 in the population, which would be 0.05, or 5% of new fish were born this month. So let's say we have a population of penguins, and there are 352 penguins. If 17 penguins die this year and 42 are born this year, what are the birth and death rates? So we're going to calculate the death rate first. We have 17 divided by 352, which gives us 0.05, or 5%. The birth rate will be 42 out of 352, or 12%. So that population would be, the birth rate is higher than the death rate, and so the population would continue to be increasing. There are 500 chipmunks in a forest with a per capita birth rate of 0.07 and a per capita death rate of 0.12. How many chipmunks are born and dying in each period? So to find the birth rate, we're going to have 500, the original population, times the per capita birth rate of 0.07, which equals 35. Then we're going to have the per capita death rate, which is 0.12 times 500, which equals 60. When we want to find the growth rate, we take the birth rate minus the death rate. So we have 0.07 minus 0.12, which is negative 0.05. So when you think about this, because there are more deaths than more births, the negative means that the population is decreasing by 5% per period. So we could be looking at per year or per month. When we look at B and D, if B is greater than D, the population is growing. If B is less than D, the population is shrinking. And if B equals D, then the population is remaining constant. So this tells us that if R is greater than 0, then this curve will go upward. And if R is less than 0, then the curve will point downward until it hits extinction. And if B equals D, we will see a straight line because the number of the population will remain the same throughout the period, either year to year or month to month. So when we look at R0, if R0 is greater than 1, the population will be increasing geometrically. So it will continue to climb and climb and climb. If it's less than 0, it will continue to go toward death. It will decrease until extinction of the population. And the larger the number of R0 is, the faster the population will increase. Well, what changes how populations grow? Well, we get this exponential versus logistic increase in the population. So unrestricted growth means that they have unlimited food, water, shelter, mates, and a lack of predation. So the population can grow unlimited. In this case, it forms a J curve, which is unrestricted growth, and it gives an exponential growth curve. So the population will continue to increase rapidly over time. When it's restricted by the environment or the availability of resources, we call that the carrying capacity of the environment. Restricted growth is a logistic growth curve, and so it's S-shaped. It will increase up until a point where it increases a little more slowly, and then it comes to its carrying capacity where it cannot increase anymore as the number of individuals in the population has reached its maximum. When we talked about carrying capacity, we think about the maximum population size based on the environment they live in. So you can see that on the right-hand side, the fish are so happy in their little fishbowl swimming around in their environment. But eventually the population becomes so large, there aren't enough resources to care for the population. So in this instance, the fish would begin to die off because there's not enough water, not enough food. They're popping out of the container or the environment that they're living in. So when we look at the carrying capacity, this is the number of organisms within a region that the environment can support sustainably so that it can sustain the population over time without losing individuals. It can sustain a maximum. The stable equilibrium is met when the population aligns with the carrying capacity line. Makes sense? Stable equilibrium, number of deaths and births are in equilibrium. Slow growth occurs right before we hit that stable equilibrium part. Fast growth is when it's a drastic birth rate greater than a death rate. The S-shaped logistic curve is formed when the growth rate decreases as the carrying capacity of the population is approached or reached. So let's look at logistic growth, which is a limited resource growth. B is the number of births in the time period. D is the number of deaths. T is time. R is the constant for the per capita growth rate, B minus D. N is the number of individuals in a population. And K is the carrying capacity. In this case, D represents delta, or that triangle we saw. So this is the change in number of individuals divided by the change in time, which equals the per capita growth rate times the number of individuals times the carrying capacity minus the number of individuals divided by the carrying capacity. So let's try this. If we have a dandelion population of 40 individuals and the environment holds a carrying capacity of 70 dandelions, if we have a per capita growth rate each month of 0.2, what is the logistic growth rate? So we look at N of the population being 40, the carrying capacity K equals 70, and the R, or the per capita growth rate, is 0.2. We plug in these numbers into our equation to solve for the change in number over time. So what is the growth rate? When we calculate this, we see that it will be 0.2 individuals in the or 0.2 as the logistic growth rate times 70 minus 4, which is 30, divided by 70 equals 0.09, or it's increasing by 9% each month. How long will the population take to reach capacity? Well, if we started with 40 and we're increasing at 9% per month, we will increase by 3.6 dandelions a month, but you can't have a 0.6 dandelion, so we have to round down to 3 dandelions per month. With 3 dandelions per month, now we can find out how many months until we reach our carrying capacity. So we take the number of individuals left to reach maximum, which was 30 dandelions. We divide that by how many dandelions are born, if you will, per month, and we get 10 months. So in 10 months, the population would reach its carrying capacity. At the end of this video, students should be able to distinguish between exponential and logistic population growth. Students should also be able to demonstrate how species interactions regulate population size.